Hello. So the next speaker is Daniel Avila. He will be talking about melting holographic mesons while cooling a magnetized quark-gluon plasma. So Daniel, it's your turn.
Thank you, Alan. And first of all, thank you for to the organizers for letting me give this little talk here. As you can see by the title, what I want to talk to you about today, it's a very interesting phenomenon that we found earlier this year. Well, since last year, but we finished the work earlier this year. We found that it's possible to melt holographic mesons by cooling magnetized quark-gluon plasma. So let's get right into it. Let me explain to you what I mean by that very funny title. So first, let me talk you about holography, strangle coupled plasmas, and magnetic fields. That is the background of our story today. As you might know, the quark-gluon plasma, or QGP, form in highly energetic particle collisions, like those at the ALRIC or the LHC experiments. It's a strongly coupled system, which means that we cannot use the usual approximations and perturbation theory that we use in quantum field theory. So instead to do that, we people have been using all these years holographic techniques to study its properties, because we can study that strongly coupled regime by solving classical gravity systems, by studying classical gravity systems. In particular, what we were interested in is that today it is widely accepted, I got the experimental fact, that for non-central collisions, a magnetic field is always present in the resulting plasma. In consequence, it is very useful to have a holographic model that can model the system, the plasma created in the collisions, in the presence of an external magnetic field. Turns out that that job was already done. Docker and Krauss in 2009 found the gravitational dual to the super young meals unequal to form plasma in the presence of an external magnetic field. That gravity dual, let me put, for this talk, I will be putting these two columns to show you the gauge theory side of things and the gravity theory side of things. So what we wanted was a gauge, in the gauge theory, was a magnetic field intensity B. So in the gravity theory side, we needed to consider a solution to Einstein-Maxwell system with a magnetic field intensity B. So that's what these nice people found back then. Also because they wanted to model a plasma, so they needed that the gauge theory state was at a finite temperature T, which from the gravity theory side of things means that one has to look to solution to these Einstein-Maxwell systems that feature a black hole. So that holographic dual describes, as I said, super young Milton equal to for plasma at finite temperature T in the presence of an external magnetic field B. So that is very nice. But there's one small caveat here. And that is that QCD, quantum chronodynamics, has quarks, and super young Milton equal to form doesn't. As you may know, all the fields in super young Milton equal to 4 are on the fundamental representation of the group, while the quarks are the fields that live in the fundamental representation. Sorry, super young Mills is adjoint representation, sorry. So we want these fields in the fundamental representations, and this plasma don't have those. So what we have to do, well, also it was well known for some years that the dictionary and the holographic dictionary entrance that give us the answer to this problem is that we want, from the gauge theory side of things, fields in the fundamental representation, which I'm going to be referring as quarks generically, with the number of flavors that we are adding being much smaller than the number of colors present in the theory. Then on the gravity theory side, what we need to do is add NF proof B7 branes in the dual geometry. And we need to study that system, to study the physics of these quarks in the plasma. So let me recap. We have this gravity dual for that magnetic plasma that we want, and we know how to add quarks. So it seems that we have all the tools that we need to study a system that's very similar to the quark-gluon plasma forming the collisions in the presence of this magnetic field. The problem is that if we try it actually to compute the embeddings of these D7 brains in the Docker and Krauss solution, turns out that the equations of motion are too complicated to be useful in practice. So that was very discouraging. So what we did, the plan was to find first another gravity dual to model this magnetic quark-gluon plasma. That's what I'm referring with MQGP. And this new gravity dual needs to be such that the D7 brains embeddings are easily computed. And we avoid the problems that rise in the Docker and Krauss solution. So we did that, actually. Turns out that the cost to simplify the proof D7 brains description was to add a scalar field to the theory. So instead of solving the Einstein-Maxwell equations, we resorted to solve Einstein-Maxwell scalar theory. From the gauge theory side of things, what we needed to do was consider a non-zero vacuum expectation value for a single trace scalar operator, which I'm going to denote as O phi. And from the gravity theory side of things, what we need to do was consider a scalar field, solutions that have a non-trivial scalar field. Turns out that even without considering flavor, even without embedding these 7 brains, which was our main goal, we started to study the properties of this new plasma because it was different from the Docker and Krauss solutions because of this scalar field. And it turns out that this plasma has very, very interesting thermodynamical properties. What we found was the existence of a critical magnetic field in these solutions. So because of the presence of the scalar operator, now exists a maximum intensity for the magnetic field, which I'm going to denote as BC, that the plasma can't hold. And if we choose to try to solve for a higher magnetic field intensity, the system becomes unstable. What I mean by that? So I am claiming that from the gauge theory side of things, this plasma is unstable if I consider magnetic field intensities above this maximum or critical magnetic field intensity. What happens in the gravity side of things is that the gravity solutions develop a naked singularity when I try to solve for higher magnetic field intensities. So that's very interesting, but we wanted to try to understand better what was happening, why this, what exactly was happening physically. So we set out to compute, among many other thermodynamical things. In particular, we computed the entropy of the plasma. We know that if we want to compute that from the gravity theory side, what we need to do is compute the area of the horizon of the solutions. So we did that. And if you have the entropy and you take the derivative of the entropy with respect of the temperature, leaving the magnetic field fixed, what you obtain is the specific heat at fixed magnetic field. And we obtain this nice curve. So this is the specific heat at fixed magnetic field. Well, that derivative is computed. And we have that as a function of different values of the magnetic field given in units of the temperature, which is temperature square. So as you can see, if we start with the plasma at 0 magnetic field, we have a finite value. This actually coincides with the usual super meson equal to 4 value. And if we start increasing the magnetic field, we go along this direction. And as you can see, it starts growing until a certain value where it starts to grow to infinity. This actually diverges at this, and here, in this case, the magnetic field, the critical magnetic field that we found is around 11 point something. So that's why I am also referring to this maximum magnetic field as a critical magnetic field, because as you can see, the specific heat diverges, which signalizes a phase transition. Before going that, let me mention something. Here we know that the system undergoes a phase transition. The problem is that we don't know to which phase it goes. With our gravity solutions, we are only able to explore the system in these values of the magnetic field from 0 to 11 point something in this case. We cannot go further. We don't know what happens for higher, which is the stable phase that the system goes. So I'm showing this plot to you so you keep in mind that everything moving forward is going to be considering only these values for the magnetic field. So that's the quick summarize of what happens to the plasma with a flavor. But let's return to that main thing. What we wanted to do was to add flavor to the plasma and study what happens to these quarks in the presence of the magnetic field. So as I already said, in order to add flavor, degrees of freedom to the plasma, what we need to do from the gauge theory side, we want these fields in the fundamental representation in the quench approximation, which is number of flavors much smaller than the number of colors. And in the gravity theory side, we need to add these NF-proof D7-branes and the geometry. So the physical parameter that is involved in all this is, from the gauge theory side, is a quark mass. We're considering fields, these quarks, that have non-zero mass. From the gravity theory side, this non-zero mass is related to the asymptotic distance of the branes at the boundary. And I'm going to denote that distance as m because it relates to the quark mass. In just a moment, I'm going to show you a nice plot where you can visualize what this distance is. So bear with me for a moment. Before showing you that plot, I want to say that what happens when you try to solve these equations of motion. So one wants to study this, the physics of this proof, these 7 branes in the geometry, in a fixed geometry. If one does that, one obtains 2 types of solutions to these equations of motion. In the first type of solutions, the branes, the D7 branes, lie completely outside of the horizon, which is what we call in these works the Minkowski embeddings. Second, the other type of solution is when the branes fall into the horizon, which is what we call a black hole embedding. So to help you visualize this, let me put a little nice plot to show you. Turns out that the results without a magnetic field are very well known and are due to David Mateos, Robert Myers, and Rowan M. Thompson, and they published a paper in 2007. So these embeddings looks more like something like this. And here I am in the r sine theta, r cosine theta plane. Here r is the usual radial ADS coordinate, and theta is one of the angles in the compact part of the 10-dimensional space. What for b equal to zero coincides with one of the angles of the 5-sphere. So what I am showing you here is the profiles of the D7 branes. This black line right here denotes the black hole horizon, the event horizon. And these 2 lines here are an example of each of one of the types of solutions that one can obtain. Here, the red line is a black hole embedding, because as you can see, it is falling into the horizon. And this blue line up here is an example of a Minkowski embedding, because it is just hanging very peacefully far from the horizon. It doesn't fall into it. As I said to you before, this distance right here, well, not exactly this one, but this little height here is what I was referring as m and previously. This is what is this distance is what's related to the quark mass of the mass of the quarks. Not exactly this, is this in infinity, which I am obviously not showing you this plot, but you can get the idea of what is this distance physically. So we have this. These are the results for b equal to zero, as I said. So now let me show you what we found. What are the results when one considers an external magnetic field? Of course, before doing that, you might be wondering what these two solutions that I just described, black hole embeddings and Minkowski embeddings, what they mean from the gauge theory perspective. So from the gravity theory, we have our Minkowski embeddings, the ones that don't fall into the horizon. From the gauge theory side of things, these things are related to, means that the gauge theory, the state of the gauge theory, we have a discrete meson spectrum. In turn, if what we are studying is a black hole embedding from the gauge theory side, that means that the state has a gapless distribution of excitations. So in this phase, the mesons are stable. They are states of a definite energy. Whereas in a black hole embedding, one have a continuum of things. One don't have a specific state with specific mass or energy. It turns out that this change from Minkowski embedding to black hole embedding happens, can be triggered if one increases the temperature of the plasma. And when one changes from this phase, the Minkowski embeddings, which are the discrete spectrum, and jumps into the black hole embedding things, when we have a gapless distribution of excitations, that actually is a first order phase transition, a thermodynamical phase transition that occurs at a critical temperature, which I'm going to denote T fundamental. So this phenomenon right here is what I was referring to in the title of the talk as melting mesons. Here we have stable mesons, and if one increases the temperature, then one stop having these stable mesons. The mesons have melted. This transition is a melting transition. That's what I was referring to. Again, this is in general. This is what was known for without a magnetic field. So let's get into the main results. Our main results. Those main results are what happens when one have a magnetic field, and it is a phenomenon that we like to call magnetic meson melting for reasons that you will see in a moment. Many of our results, turns out, can be neatly summarized in the following phase diagram. So here I'm showing you the phase diagram of the plasma. This direction, it's the magnetic field intensity given in units of the mass of the quarks. And below here, we have the temperature of the plasma given again in units of the mass of the quarks. So I'm working at fixed quark mass and moving the temperature and the magnetic field intensity. So let me describe what we have here. This red line right here, it's dividing the phase diagram into sections. The section up here is non-accessible, meaning what I was saying about the backgrounds without the flavors. These magnetic field intensities right here are above the critical one for the corresponding temperature down here. So what I mean by non-accessible is that with the gravity setup that I just described, we cannot explore this part of the system. These intensities are above the critical magnetic field intensity. So this red line divides that. But we can, without much problem, analyze what happens in the right-hand side of the diagram. On the right-hand side, we have this blue line. What this blue line does is separate these sections in the region where we have black hole embeddings and the region where we have Minkowski embeddings. Remember, in terms of what's happening in the gauge theory side, this means that this region outside of this blue line right here, we have the mesons are dissociated. We don't have stable mesons. And in this region inside here, inside this the blue curve, we have stable mesons. This blue line actually it's denoting the coexisting phase region because this is a first order phase transition, as I'm going to show you. And so that's what denotes this blue line. So looks like everything is pretty normal. What I mean normal compared to the case without a magnetic field. When we look, for example, at the results at b equal to 0, we have the situation that I previously explained. For low temperatures, we have stable mesons. If one starts increasing the temperature, and we go right here, at some point, the mesons start melting here. And then we have the mesons are dissociated in this region. So if you look, for example, at what happens with the system when we consider a magnetic field intensity equal to 1, and we're in this line right here, we have exactly the same situation, starting obviously from the accessible part. We have stable mesons for low temperatures, and we have melted mesons for high temperatures. But take a look at this part of the plot. We have this blue curve has a maximum right here, and we have this little region here. So it's very interesting what happens there. So let me make a zoom of this part. Let us look closer at the most interesting region. The same phase diagram, I'm just making a zoom. We have again the magnetic field, the temperature, then an accessible region. And we have the two regions we can study, the one with the stable mesons and the one with mesons dissociated. So look, for example, at what's happening when we fixed our magnetic field intensity equal to 3.4, and we are in this line right here. And let us start, for example, at a temperature equal to 0.6 here. If we start here and then we start increasing the temperature, we are moving in this direction. At what point we reach the critical temperature and the mesons melt. The mesons melted when we increased the temperature, which is exactly what we expected. But now look in the left direction. We start at 0.6 and then we start lowering the temperature. So we are moving into this direction. At some point, we're going to reach a critical temperature, which is lower than this critical temperature right here. And if we keep reducing the temperature, the mesons again they dissociate. They're stopped being stable mesons. So again, the mesons melted. That's what I meant in the title of the talk when I said that we melted the mesons by cooling. This is melting by cooling. We can melt the mesons by reducing the temperature of the plasma. For certain magnetic field intensities, as you can see, we need to be in this region that goes from more or less 3 to 3.5, 3.4 something. I don't have the explicit numbers in the presentation. I have them in the paper, of course. We just focus on the regions. We have this very interesting phenomenon. Sadly, we have this red line here, which don't allow us to study what's happening with our gravity solutions. So we cannot answer what exactly happens in this site if we keep decreasing the temperature. But nonetheless, this right here is very, very interesting. So another thing that I want you to look at this, to note from this plot is that also something that can happen. Imagine now that we are working at a fixed temperature. Imagine we are again at 0.6, and we start with a magnetic field intensity equal to 3. If we leave the temperature fixed and instead we increase the magnetic field intensity, then we're moving in this vertical direction. We are going to eventually reach a critical magnetic field, which is not the same as this critical magnetic field right here, more like a critical fundamental magnetic field that has to do with the fundamental degrees of freedom. That if we keep increasing the magnetic field, the mesons again melts. We can melt the mesons also at a fixed temperature, but by changing the magnetic field intensity of the plasma, which is also very interesting. So let me summarize what I just said from the diagram. So point number 1, the mesons can be melted at fixed temperature and quark mass by changing the intensity of the magnetic field. And for certain values of the intensity of the magnetic field, we have now 3 phases depending on the values of the temperature. We have the hot black hole embeddings, which are the usual black hole embeddings. We have the Minkowski embeddings at intermediate temperatures, and for low temperatures we have these new cold black hole embeddings, this new cold phase. Which also reminds me, I want to make very clear we're still dealing with plasma. So this, even if I am using the words cold, for example, that doesn't mean that we are working with a few kelvins. No. We are still on the very hot temperatures of the usual plasma. I'm using the word cold to refer to cold with respect of the temperatures of the b equal to 0 case. So these are the main results that we can read from our phase diagram. What I also wanted to show you today is that we also studied the quark condensate. And the quark condensate is one of the most important observables in the magnetic quark-gluon plasma. It is very important to know how the quark condensate behaves as a function of the magnetic field and the temperature. And we can do that with our holographic model. What we want is to study the behavior of the quark condensate, which is this expectation value, these operators. From the gravity theory side of things, what we need to do to study this thing is to compute the variation of the on-shell action with respect to the quark mass. If we do that, we can obtain these plots. Here I am showing you the quark condensate given again in units of the mass of the quarks. And down here, we have that as a function of the temperature. And each one of these lines of different colors correspond to a different fixed magnetic field intensity. So the red one up here corresponds to b equal to 0. This is the well-known b equal to 0 case. If we move down here, we start increasing the magnetic field until we reach the purple line, which corresponds to b equal to 3.4. So as you can see, the general effect of the magnetic field is to lower the value, the magnitude. It's to lower the value of the quark condensate, but given this, this is just a signature convention. What it's actually happening is that we're increasing the magnitude of the quark condensate when we increase the magnetic field. So one observation is that for any magnetic field different other than 0, we have a non-zero quark condensate. That means that that chiral symmetry is always broken in this plasma that we're studying. And also what I just said, that the magnitude of the quark condensate increases as we increase the intensity of the magnetic field. That is what is known as a magnetic catalysis. That result is consistent with some some lattice results. That actually that happens, that we have magnetic catalysis for these values of the magnetic field and quark mass. Also, something that we can read from these plots of the quark condensate is that the melting transition, be the hot, well-known phase transition, or this new cold phase transition, in all cases, we are dealing with a first order phase transition, regardless of the magnetic field. To show you that, for example, we can make a zoom at the green curve that I showed you before, near the transition region. So here on the left hand of the right hand side, I'm showing you the quark condensate as a function of the temperature for this particular magnetic field, which I think is 3.3 or something like that. The dashed line corresponds to the Minkowski phase, and the continuous line corresponds to the black hole phase. So as you can see, this is the region where this region of temperatures here and here is where both types of embeddings can coexist. This is the coexistent phase region. And this shape right here that is displayed in the quark condensate is the usual shape of a first order phase transition. Because this is the first, the variation of the action. The initial action is related to the free energy of the system. So the quark mass is one of the derivatives of the thermodynamic potential. So this form of one of the derivatives of the thermodynamic potential is related to this to a phase transition of first order. On the left-hand side, I'm showing you the exact the transition region, but for the cold case. So you can see the temperatures that I am displaying here are 0.55 something, and the temperatures here in the plot on the right hand, it's 0.6. So this is the hot phase transition, and this is the cold phase transition. But again, the shape is the same. It still displays the usual shape of this first order phase transition. What else did we do? We also performed a thermodynamic analysis of the plasma and computed the meson spectrum. So I'm not going to go on much detail on these results. You can check them on the paper, or we can discuss them later. But let me summarize some the important parts of this. We performed then a full thermodynamic analysis of the system, which means that we computed the free energy of the system, we computed the entropy of the system, and we computed the internal energy of the system. By computing these three quantities, we, in all cases, found that the system is thermodynamically stable when one considers that one needs to study the full system, that being the flavor degrees of freedom and the color degrees of freedom, that is the plasma without the quarks. We also computed the meson spectrum as a function of the magnetic field. We have some nice plots of that. The main lesson that we draw from that computation is that the magnetic field B imposed restrictions over the quantum numbers of the meson states. So compared to the B equal to 0 cases, we have actually less states, even by less options in the quantum numbers of the mesons. And also that the general effect of the magnetic field is to decrease the masses of the mesons. In particular, it also decreases the mass gap of these things. So let me finish by stating some conclusions. So the first one is that we found this gravity dual to the magnetic quark-gluon plasma that allows for the inclusion of flavor degrees of freedom. Something that I didn't mention actually, and it's very, 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 very important, is that this holographic model is a top-down model. We solved the full supergravity to 2B 10-dimensional equations. And that's how because we needed to embed these 7 branes in this geometry. The second conclusion is that we found that there exists a maximum intensity for the magnetic field, this critical magnetic field, above which the system becomes unstable. The main lessons we learn by studying the flavor degrees of freedom is that mesons can be melted at fixed temperature and quark mass by changing the intensity of the magnetic field. And the one that refers to the title of the talk is that for certain magnetic field intensities, the mesons can be melted by heating or cooling the plasma, which was very shocking. And that's all for my part. Thank you for your attention, you all.
Okay, thanks, Daniel, for the nice talk. Are there any questions? Carlos, do you have a question?
Yeah. Let me ask one and then keep others. Thanks for the interesting talk, Daniel.
Thank you.
So, Daniel, okay, I wrote many. Let me ask one. Let me ask the first that I wrote. Okay. In the beginning, you mentioned something about adding scalar probe, right? Instead of a D7, but then you mentioned that you added a D7. You have a full geometry and you added a D7, right?
Yeah.
So I didn't understand the thing of the scalar probe, the scalar field, and why what that teaches you regarding the flavor degrees of freedom.
Yeah, maybe that was I explained that a bit confusing. In the original gravity dual that Docker and Krauss had, they only considered this gravity solution that have a magnetic field and the metric, and that was it. We tried to embed these 7 branes in the geometries, but the problem is that the equations of motion were too complicated. So what we did was return to the drawing board and think, okay, this gravity dual, it's too complicated to do that. What we can modify in order to make the embedding more simple, the equations more the equation to be more easily solved. So what we realized is that if we modify that theory, and instead of just considering as a gravity dual with the metric and the magnetic field turn output, we also consider a non-trivial scalar field, then the geometry simplifies, and we can embed the D7 branes. What I mean by that is that scalar field is not a proof. That scalar field, it's fully retroacting on the geometry. It's a full gravity solution with metric, magnetic field, and scalar field. So I have that metric. And on top of that metric, I consider the D7 brane embeddings.
Okay, so it's not only Young-Mills with magnetic field, but also this scalar field is doing something else.
Yeah, the way the scalar field is, let me return to that. It's around here. So in the gravity theory, as I said, what we need to do was consider these solutions that have a non-trivial scalar field. In the gauge theory side, that scalar field is related to considering a non-zero expectation value of one single trace scalar operator. So I'm not adding a different field to super Young-Mills.
You are putting Young-Mills in a particular vacuum. Very good. Very good.
Exactly.
Look, I'll let people ask. If not, I'll have another. But let me give people the opportunity to ask.
Perfect. Let's see.
This solution of that you use, does it preserve without the black hole? Does it preserve any SUSY?
That is the thing. Without the black hole, then I am considering a solution with temperature equal to 0 and a non-zero magnetic field. That falls into the kind of solution that we couldn't find, that we didn't find.
Okay,
we can study.
It's only with the black hole that you find the solution. I see.
Yep, actually.
I see. Okay. One comment about just terminology. It's a minor comment.
Yes.
Here you're using the word melting, right? Because David and Myers used that word at some point, but it's just that the degrees of freedom become somewhat deconfined, right? So the strings that before were both of them on the probe now can snap into the black hole, right? It's not them melting like the water or the ice melts, right?
Yep.
And so in this sense, it's not that odd that you could lower the temperature and still have melting, right?
Yeah. Actually, yeah, that title that maybe
no.
It's a bit extreme to use.
It's the word that people use, but
yeah.
Okay, nothing. I'll leave the rest for the discussion session.
Perfect. Thank you.
Okay, I guess any other question can be left for the discussion session.
Okay, perfect.
Nice. Thank you very much, Daniel.
Thank you, Joel. Let me stop sharing.